circle, and do all an hour ago.
What?
So chapter 12, mass storage systems. We talked about file and, file interface and file implementation. I did assign a homework. I apparently just didn't go over it. Or maybe I didn't do something. Did y'all hear about homework 7? Did anyone do homework 7?
That was from, I don't know. I think that was like last week or something.
It was due today, right?
Homework 6 was the last one on the previous section.
Okay, so I'll give you another week on homework 7. I don't know if I thought I went over it. Let's go look real quick.
Homework 7 was 21 days ago, so.
Yeah, I turned in homework 7.
Oh no, I'm talking about homework 8.
You turned in homework 8 too?
Yeah, this one. Files, pros and cons.
You went over it last class.
I did? Okay.
That's homework, which is that 8 or 7?
I don't know that you went over it.
Yeah, I don't think you went over
Yeah,
it.
you pushed it.
Okay, so do homework 8, chapter 10 and 11. I'll give you a little extra time because I do believe I skipped over it and didn't make it clear when it was due, plus midterm, et cetera, et cetera. But yeah, this is just going over files, the implementation, and the interface of file systems. 10 questions. Hopefully none of them are out of the ordinary. Right now I have it, when's that, October 19th? What's today?
Well, it is 12.
Okay, so you have 7 days. Good. I got that right.
One of them was a little weird.
All right, but back to our actual discussion. Mass storage system. So we talked about files, file implementation. I think logically next comes how do we store these, I guess, from a hardware and OS standpoint, how do we store large amounts of data, aka mass storage systems? Are there going to be different attributes to help us out here? Hopefully y'all can realize that the answer is yes. When you start getting into very large systems, certain problems will start arising. So that's what we're going to talk about today. Yay, look at the overview. The big thing today is RAID. RAID's a very important feature in mass storage devices, as well as other features. I think if you understand RAID, a lot of other things make a lot of sense. So your homework actually has 3 RAID problems, so make sure you pay attention to that part, even though it's going to be fairly short. All right, that's nice. Okay. Mass storage systems. So this is still kind of an odd time to be discussing this because most systems that are mass storage still use magnetic disks, although solid state drives are been just steadily eating away the I guess the storage space. Although it's starting to look like it's going to even out and that a lot of mass storage will still be the conventional spinning disk as opposed to, or spinning magnetic disk as I like to call it, as opposed to SSDs for several reasons, mainly that the magnetic hard drives are still cheaper, and when you use a lot of them in conjunction, the performance can actually be better than using a solid state drive depending on your situation.
And solid state drive, degeneration.
And yeah, you have a lot of degeneration with solid state drives, so there's a lot of use writing and rewriting. Again, your magnetic disk will actually be superior in that regard because, yeah, solid state, you can only do it so many times. And there's a couple other things. So we are still going to go through magnetic disks, even though for a while there it looked like they were going to go to the wayside. I think nowadays it looks like they are going to hang around, at least in large data center applications.
Well, we still have reels or the tape.
Yes, we still have tape.
Are they still trying? Have they given up on the idea of transferring the tape to disks?
People have not given up on it. Companies have not. But the reasons to keep tape backups are quickly disappearing. So I would be surprised if tapes were still around as commonly today. In 10 years, I don't think they're going to be as common as they are today.
No, they won't be as common for backups, but they will still be there in archive because there's some stuff that you're just not going to touch, but you still want the information.
Right. The other problem with tapes is they still degrade. They have a shelf life.
Yes.
And also a lot nowadays when you can do so many distributed systems and backing things up, and magnetic storage is what's kind of replacing tape, as you know, as SSDs are kind of replacing magnetic, or I should say, spinning disk. The spinning disks are starting to really replace all the tape as well. Tape can still hold more, but the cost is not as big as it used to be. These slides are a little old. This is 2009, so these are 8 years old. So a couple things have changed. I'll try and point those out as I go through today. But all right, bless you. So magnetic disks provide bulk of the standard storage. Well, back when this was written, definitely of modern computers. Nowadays, most desktop machines use a solid state drive. Anyone here still have a spinning disk in their laptop? You do?
Oh, and my laptop? No.
No, not at all. You?
Desktop, I do.
Ooh, ew.
I have 2 of them rated together.
Nice. Which RAID?
1.
1. So they're mirrored?
No, 2 then. Or 0.
0 is when they're striped. Did they make one giant? Oh, okay. All right, we'll talk.
0 sucks.
Not necessarily.
When it goes down, and
Well, let's
and
get to that.
I made a stupid thing. I bought 2 of the exact same type of drives at the exact same time from the same manufacturer.
All right, let's save it for there, okay? All right, we gotta get going. Let's follow the thought process. All right, first, mass storage, spinning disk. That's what we're going to talk about for large-scale mass storage. Yes, spinning disk is still the primary source. Drives rotate, was it 20 to 200 times per second? If you actually think about that, that is pretty slow, really slow, compared to how quickly a CPU operates at gigahertz, so nanoseconds, and this is going to take, was it 1/60th of a second? So you're still in the millisecond range. It goes milli, micro, nano, and actually it's sub-nano on a CPU, so that's pico. Yeah, so it's really slow. Transfer rate data is how it flows from one to another. Position time, this is for random access, how to move the arm to the desired cylinder, which is seek time, and then of course your disk has to rotate to the correct location. And then a head crash results from the disk head making contact with the disk surface. They say that's bad. Why is that bad?
Scratches it. Just
Scratch it and destroys it. Yeah, not a good day. But disks can be removable. A lot of systems actually have them hot removable. While the system's running, you can pull it and put a new one back in, and it's good to go. Well, put it in, it does some stuff, and then it's good to go. Good to go.
Load it back up.
Right. Well, you even have them going through USB nowadays, and that's been around for a while. Buses vary. Y'all probably haven't heard of EID in a long time. Those were those old ribbon cables. ATA, which, again, sometimes old ribbon cables. SATA is the new one. Hopefully y'all have seen the little SATA connectors. USB, that's what we're used to. Fiber cabling, and then SCSI. SCSI can be all sorts of different things. But SCSI has always been thought of as more of the high-speed version of these interfaces. But it's very old, but it's been updated a lot. And the host control is what actually controls the disk. Or talk to the disk controller, I'm sorry. The host controller is in the computer, talking to the disk controller that's on your actual hard drive, that then's what's controlling your hard drive. All right, good old picture. All right, what can we say about this? All right, it rotates, so it's spinning. This one's spinning clockwise. Notice that they have 2 arms in this picture, so you can read the top and the bottom of each disk. Notice that they're then divided into tracks, which is one full circle, and then a sector is one of those blocks on a track, and then we got a whole cylinder is basically the up and down of the whole sector. Why would we want to look at the cylinder? So
It's faster access time for your information, because let's say you have 3 parts of a paragraph. It's on track 1, 3, and 5. Then you're looking right over the same.
Yeah, if all your
same
arms
spot.
are on the same spot,
Yeah.
you can read multiple sectors at the same time.
Yeah.
So you have a multi-disc hard drive, then you can read multiple sectors at the same
If you
time.
had to use 3 sectors side by side, then you have to wait for it to move. scan.
Right.
move.
Right. Yeah. And then those other arms are doing nothing. So you can actually look it up. Some hard drives only have one platter or disk. Some of them will have multiple platters in them, depending on what you're using them for. Okay, then there's also magnetic tape. This was probably the earliest second storage, or one of the earliest, I'll say. Holds large quantities of data. It still holds more than magnetic disk, but the access time is slow. And then there's random access, which is absolutely terrible. Why is that random access terrible?
Because it's got to move the tape to that location.
Yeah, if you remember, you got to rewind the tape or fast forward the whole tape just to get to the right sector. You can't, at least in a disk, you can move the arm and skip tracks. Here, you got to go through the whole tape. So this is really only used for backups because you're really just dumping the whole disk to a tape. Makes sense. And then read it back. 20 to 200 gigabyte typical storage. Wow, that's an old slide. Yeah, they're usually more like, I don't know, 20 terabytes or 30 terabytes or something. Not this. And yeah, they have different technologies on them. All right, transfer rate can be very convoluted on how you actually calculate this. But hopefully you can see that the maximal transfer rate occurs with sequential access because you're trying to read each sector one at a time as the disk is spinning across the arm. Hopefully that's pretty obvious. The average time to access something, well, you got to figure out what's the average to seek to it, to the correct track. What's the average time to rotate to it, and then what's the average transfer to actually read that data. Well, seek time is to the position head over the cylinder. So if you want to just take the average of where you need to move your arm, that would be your average there. And then once your head's in the right location, you have to wait for the disk to spin to the correct location. So it's probably, it's halfway around. We'll just say for the sake of argument. And then you can multiply that out to figure out what the average rotation is. And then transfer is however quickly. That also depends on your rotation, as well as how big your sectors are and how much data you can read. All right. Any of this?
And transfer time is the smallest because it's usually just moving electrical signal from one to the other.
Right. Right.
And rotational. So the seek time is the
time to position your head, that arm, to the correct
longest
track.
part of your time.
Usually, yes. Yeah, because your discs are spinning really fast. Well, compared to your arm. They're still spinning incredibly slowly compared to your CPU. And then transfer time to actually read it. Again, while this is the fastest, it's still ridiculously slow compared to your CPU because you're waiting on actual physical movement. In other words, the physical world is really, really slow. All right. Why would sequential access often not be possible? Think of our file systems and how they're laid out. Even in a contiguous one, this would be great because they're all right next to each other. But as we discussed, contiguous file system implementation is actually kind of bad, pretty bad compared to what you need to do, especially if you need to read and write or append something. You may have to transfer the whole file again, and you have a lot of fragmentation. You're not utilizing it. So most of the time, you have some type of linked implementation or inode implementation, which means that while you may read one block, you then got to jump to all these other blocks to find the rest of the file. So usually the file contents become scattered, hence why they use something called a defragmentation utility to try to organize it so they're all next to each other, and then you can read it a lot faster. And then recent hard drives have a lot of onboard cache. You'll probably see it's like 4 megs onboard cache. In other words, your most recently read, they'll just store it in the memory on the disk. So when you ask to read it again, it can just give it to you as opposed to doing this whole physical thing again. Everything here? Good here?
So even disk have cache.
Yes. Yes, even disks have cache. If you have a performance problem, what's the first thing you do?
Cache.
Cache it. It's like it's just the solution to everything. It seems like sometimes. All right, capacity. Vendors express capacity in units of GB, gigabytes, where 1 gigabyte is 10 to the 9th. Why is that confusing? what is it really?
124.
Well, no, to gigabytes.
No.
So it's really
4 to the 4th.
Sure, or to the 4th?
10.
Wouldn't that be to the 3rd? Because it goes kilo,
Yeah, to the 3rd.
mega, giga, yeah. Or just 2 to the 30th.
Sure, if you want to take the easy way out.
Why would you make this more difficult? And if you actually multiply that out, it's not 10 to the 9th. So that can be confusing, but they're just trying to sell their products. Capacity is determined by, yes, recording density, track density, and aerial density, product recording and track density. Oh, right, so number of bits that can be squeezed into 1 inch, the track number of tracks that can be squeezed into 1 inch of radial, and then aerial density has a lot to do with the size. The both of those combined. All right, sure, we partition them into something called recording zones. Wow, we're doing a lot of hardware today. All right, a disk you can think of as just memory. We think of memory as just one long contiguous array of bytes. Disk, it's the same thing. We just call it logical blocks for a hard drive. Sector 0 is the first sector on the outermost cylinder. And then it proceeds all the way in through the innermost. All right. There are different ways to attach, or different interfaces to attach a hard drive. We talked a little bit about with EID, ATA, serial ATA, and SCSI. SCSI is a bus. What was that? Small computer system interface. There we go. You can have up to 8 logical units, aka 8 disks attached to it. EIDE, I think you could only have 2. Serial ATA, it's serial, so you really only have 1, but you can have your controller just control each one individually. There are other ones as well for a high-speed serial architecture. So you have storage area networks. And I think we're going to get a good picture of why that's important. And then can be arbitrated loop. There's other ones as well. Now, I said storage area network, so before I explain why that one came about, let's look at network attached storage. So in a network attached storage, NAS, you have your different clients, and they're connected to your NAS device via your LAN or your WAN, your Ethernet network connection. Just throwing acronyms out right now. It's usually done NFS or CIFS, more CIFS nowadays. There is an iSCSI, which takes the SCSI protocol and does it again through Ethernet. What do you think is the problem with this architecture? Or what do you think we could do to improve it? Why is it slow?
Because it's got to go across the internet.
Well, not necessarily the internet. It could go across the LAN.
Sure.
All right, it's slower. What can we do to speed it up?
Fiber optics.
Fiber optics. I was waiting for you to say add a cache.
That was my next guess.
What is Ethernet used for?
Communication.
What type of communication?
Point to point.
Point to point, okay. Yes. Any particular point or point to, okay, that's fine. Any particular type of communication? Web traffic, file transfer,
All of the above.
all the above. So it's a general purpose data connection.
Yes.
So what could we, if it's general purpose, we can instead make a,
Specialized.
oh, there we go. Wow, all right. That's what a SAN is. It's the same thing, only the network is specialized for attaching storage to different systems. So if you actually look up how a storage area network works, it's going to have a lot of protocols or interfaces specifically for data transfer. So usually, and by usually I mean pretty much always, it is faster.
By a speed factor of.
That's a great question. I don't know off the top of my head.
Okay.
Also, the other reason,
We're introducing, okay, well, we have our clients, we're the client, right? When we're going through the land to get to the mass storage. And before, we just went through the land to do mass, to put it through mass storage like there, right? Right? And we're saying, okay, now that's slow. Now we're going to increase it by increasing the interfaces between us and the mass storage.
so this is a terrible picture, because in reality, there should be a wall of servers right here. So the client's still always talking to a server, which then goes to a NAS.
Okay, gotcha.
Over here, we're actually dividing it out. So you talk to one to the server and then another one to the backbone. The other thing to keep in mind is that if when you have your servers here, they're still sharing the LAN with the clients. So there could be traffic issues as well. Over here, by making it specifically separate, which you could do.
At that point, basically, the servers have passed off the data to be saved.
Or read.
And then we give the specialized servers.
Right.
Are those servers in there, are those supposed to represent the same servers we were dealing with before, or they're just specialized?
Yeah, we'll just call them. We'll pretend that this all existed except for this LAN and WAN and that LAN and WAN were the same thing.
Okay, so now, once we pass off our data to be saved, we could care less, we're no longer interacting. The server itself then is interacting with the specialized
Right.
network.
Right.
And they're only doing data transfer.
That's it.
But it still has to go across the land to get back to the client.
Correct.
But we're not taking up land resources in order to do our storage.
Right. This is the point. The only point of this is that by making a separate network specialized for data transfer, you can gain some efficiencies. And if you want to go look up how SAN works, go right ahead. Because that's it. That's all we're going to talk about here. Okay. Disk scheduling. Is anyone surprised that the word scheduling didn't come back? Not all? So, the OS is responsible for using hardware efficiently. Oh boy. For disk drives. This means having a fast access time and disk bandwidth. How hard do you think this problem is? Is this going to be
Time
easy?
And large bandwidth, not very
Not very
easy.
easy? Oh, okay. Yeah. The key word that always makes this hard for OS people is the word efficiently. Oh, man. If we just had to do it, that'd be fine. But now it's got to be efficient. All right. Access time is two components, your seek time, your rotational. So we want to minimize the seek time. Usually it's the seek distance, roughly. It's proportional is what we're basically saying, because your arm is going to spin or move at a constant rate, so really it's the distance. So you want to try and minimize the distance you need to seek. Bandwidth, total number of bytes transferred divided by total time for the first request to service and the completion of the last request.
So keep the majority of the data in the middle of this.
All right. So, several algorithms exist to schedule the servicing of a disk I/O request. Is anyone surprised by that statement? Not at all. Good.
Which means we don't use any of them.
Yep.
We ignore the problem.
And they're probably going to be in the homework still about.
I am glad you understand how this class works. Perfect. Beautiful. I didn't have to say it. Thank you, Matt. All right, so we're going to have an access queue. We'll say we have from 0 to 199. We're just going to say blocks. Or tracks, whichever you want to think. The head pointer starts at track 53. We need to go to 93, 183, 37, 122, 14, 128, 65, and 67. Those are what we need to do. So what would be the first type of algorithm to do?
First come, first
Go
served.
back. Yeah, sure.
So first come, first serve. Starts at 53. Go to 98, all the way to 140, 183, all the way back to 37, all the way over to 122, all the way back to 14, all the way over to 124. Then we can go back to what? 65 and 76. So do you think this was fast, or this? I don't know. This long horizontal line fast.
The long one.
The long. In other words, in this picture, anytime you want to minimize your horizontal distance is what we're trying to minimize. And I said distance, not displacement. So it's your total travel time horizontally. So as you can see, this one you're jumping around a lot, probably not the best thing. So what would be another one?
Move the head to 0 and shortest number first.
All right, that's good. You combine two different ones. We're going to do the shortest. I already forgot what the second S stood for.
This one must be super
Shortest
important.
sector.
No, seek.
Seek. What's it?
Shortest seek time.
Shortest seek time first. Thank you. Okay, just go to the closest sector. All right, here we go. So you're 53. Which one's the shortest? 65, then 67. Next is 37, then 14. Oh, we gotta jump all the way to 98. 122, 124, 183. All right. Does that at least look better than the previous one?
Yes, it's less.
Yeah. What's an issue with this?
It still has that one really long jump.
Has one really long jump, but what's even worse? Let's say, think about a large
It
system.
goes in 2 different directions.
You can go in 2 different directions, which isn't that bad.
Starts this way, then this way, then this way.
Okay, yeah, there are a couple of issues with that, but
If you add a new task,
mhm.
then that may change the direction and the distance.
So you think about this from a standpoint of your queue will always have items in it. You're constantly getting requests.
Oh,
Maybe your
okay.
queue is always full. What could happen?
Starvation.
Starvation. Why?
Because the thing that is furthest away from where their head currently sits might not ever get serviced if we keep getting things near the head.
Right. Y'all see that?
Yeah.
If we're over here at 53, we'll say less than 98, and we're just bouncing around over here in 98, 183 may never get serviced. All right. What would be another one? Now you started it. I liked it. So we have
0 to the end constantly.
Yeah, there you go. So that's a good one. That's a good one. That's another algorithm. I'll ask you which one's the best in a while, but y'all already know the answer to that question, I hope. The disk arm starts at one end of the disk and moves towards the other end, servicing until it gets to the end of the disk, where it moves in reverse and continuing servicing. Sometimes called the elevator algorithm, because it's an elevator, goes all up and then back down, up and down. All right, so we'll start 53, go to the beginning, then go all the way over. So is this better than first come, first serve?
Probably not.
It's a little better than first come, first serve. Let's look at this picture and then let's look at this other one.
Okay.
Yeah.
Less travel distance.
Yeah,
Okay.
definitely less horizontal travel distance. Do we have
it
stuff?
guarantees that you will finish your.
Right. Is there starvation?
No.
No, there's no starvation because it's going to eventually get to whatever you need. Okay, great. So C-scan is just going to change this up a little bit. From the head again moves from one end of the disk to the other. However, when it reaches the other end, it immediately returns to the beginning of the disk and starts a return trip. Why would you want to do that?
Because it's been the longest time since we serviced.
Right. So we want this supposed to some idea of fairness, where you go all the way one way and then you start over, so you're not. I guess what's the word? Biased for the edges. All right. Is this better than first come, first serve?
Yes.
It still is, although you have this one horrible horizontal change. Maybe we could actually make a piece of hardware that, okay, you're going to the beginning, zip, something that would make that a little faster. Maybe we could add that in to help.
Well, you could hardware-wise, you could say, okay, I've got 2 heads. I'll keep one at 0, and the other one goes through a thing. And as soon as I'm done, I've reached the end, initiate the other one, and meanwhile I'm swinging that one back. So you're not using your
True,
resources.
but most of the time you want your 2 heads where they are because you're going to be reading a lot of sectors, so it'll increase your transfer time if they're in sync.
Okay, gotcha. Never mind.
But I see what you're trying to get at. I understand. Just
Back with hardware.
yeah.
And
Okay.
it's on the other side.
Hmm?
And it's on the other side.
The heads on the other side. Oh, have 2 of them. Yeah, we could do that. Hold on a
I
second.
just have $1 million idea.
Hold on a second. Hold on. No. There's going to be. So you have the track. It's going to go like this. No, there's no place to put the other head.
What do you mean?
Physically, there's no place to put them. They would get in.
By the same space and then.
They would get into each other's. They would hit each other. So the arm would hit the other arm.
No, they'd be exactly opposite of each other.
Yeah, this isn't where the arm has to go across the whole disk for it to work correctly, physics. If you just have it in the beginning, that doesn't work out too.
Isn't there a cylinder in the middle?
Is there a cylinder in the middle? There's a spindle in the middle, yes.
Right, that they can't go through.
Right.
So they don't need to go across the whole disc, they just need to go across half the disc. And the other one only needs to go across half the disc.
All right. Remind me to show you a picture of this and it'll make sense.
Okay. Show me a picture of this so it can make sense. I
Later.
reminded you.
All right. Then there's something called look. Arm only goes as far as the last request in each direction and then reverses immediately without going all the way to the end of the disk. All right, so we don't have to go to the end of the disk. We shave off a little seek time. And then we're going to improve upon that by, instead of going reversing, we'll do the C look where it just goes all the way back to the beginning, but it's service the highest request and then it goes to the lowest request. So it's shaving off a little these two edges, some seek time, so to speak. All right, which one's best?
The one you haven't shown us yet.
I've showed you all the ones I'm going to.
If you could
Either look or see look.
Wow. Come on, guys.
Does it depend?
Thank you. It came out, finally. Technically, it depends. Although shortest seek time first is common and has a natural appeal because it's pretty easy to implement, but you have a starvation problem. S-scan and C-scan perform better for systems under heavy load. If you know that your queue is going to be empty at some point, then shortest seek time first is probably a good algorithm because you're going to eventually service everything. Under heavy loads, which is usually what these disks are going to be used for nowadays, you probably want scan or C-scan. It really depends on your requests. So there's that word, depends. I think I'm going to have a final exam question of what type of problems do we solve and what's our usual solution?
I think I
Depends.
Put it depends. Didn't I put like it depends for like half of my midterm?
I hope so.
Well, just even that one, the one question had about, well, which cache should you use? Well, it depends. If you have money.
Let's see.
In fact, I think that's why I missed like half of my midterm questions because I put it depends and then I tried to clarify my it depends. I should have just left it depends.
That's your it depends.
Move on.
Or we ignore this problem because it's too hard, right? Those are your two answers for the whole midterm. Don't do that. But that's funny. All right. Second to last bullet point's important. Keep in mind that your scheduling algorithm is usually a separate module inside of your operating system, so you can change it out. Shortest seek time first or look is a reasonable choice for your default algorithm. Notice that by the implication here is that at some point that may change.
Does the user select the algorithm or does the operator system select the algorithm?
Whoa. What's the answer to Chris's question?
It depends.
Okay, good. Yeah, we're doing great. Go ahead.
So either the SSD, so shortest seek time first, you're going along with shortest seek time first, and then let's say you have some sort of counter or something, and you're saying, yeah, I have some things that have not been but percentages that hasn't been covered of the disk.
Yeah, we'll just switch to look for a while.
Just to switch to look, just to make sure, or even just switch it for just enough so that you can cover
A time slice.
starvation problems.
A time slice, yeah.
90% SSTF, 10% scan.
Sure. Right. The point of this is you can, switch between modules. All right. I really wish this slides would help me jump from one giant section to another, because now we're going to talk about disk management, different than disk scheduling. So management is how do we actually store these partitions on the disk. So a partition is one or more groups of cylinders. The logical formatting is aka making a file system. And we also have a bootstrap or a bootloader program that's usually, there's a part that's stored in ROM and then another part that's stored in the hard drive. And then there's something called sector sparing. If you have bad blocks, maybe you can use a different sector instead on your hard drive. Okay, common or classical partition scheme, I will say, inside of a hard drive. This was definitely used by Windows 2000 and pretty much all Microsoft operating systems beforehand. Linux can use this one, or it can use the EFI method as well. We're just going to look at this one because it's simple. The next one's just a more advanced version of this. But the point of this is that your disk has essentially 5 partitions, but partition 0 is your master boot record, which is a very small amount of space. I forgot the exact size, but it's in kilobytes. And that'll contain your boot code. If you want to boot from this hard drive, just the straight hard drive, it'll have a piece of code of what to start booting from. And then it'll have a partition table telling you where partition 1, 2, 3, and 4 are. And usually it has an extra 2 bytes to signify the type of file system that's supposed to be stored there, so you can actually do something with it. So very common boot code might be, all right, go to partition 3, read these blocks into memory at memory address 0, then start execution at memory address 0. AKA read your kernel in, start execution. Did we talk about something else? No. Okay. So technically your hard drive has 4 partitions, but you are actually allowed to partition it more. Can anyone take a guess on how we do that?
Partition the partitions.
We partition the partitions, right. So these are called primary partitions, and you can partition a partition with something called an extended partition. So partition 4 may map to any number of partitions, aka you take this partition table and put it at the beginning of the partition. All right. Any other partition questions? Good. All right, swap space. As we mentioned earlier, usually you have a partition dedicated to your swap space. Unless you're Windows and you just have a swap file. Every other OS has usually a swap space. Usually
a swap file.
Windows has a swap file. They usually store it as a swap file on their NTFS file system. Other operating systems will have a separate partition with a special formatting specifically built for swapping processes in and out. And the reason for this, for example, what Linux does is you might have a swap map, and then your area is just going to be page slots for aka the pages you have in memory. We'll just write it as pages to your swap partition. So there's an easy mapping, very simple, straightforward, where you write it to. And that's why usually it's a separate partition, because the file system, what you're storing is very straightforward. You're storing pages. All right, let's stop here before we go into RAID.
That was Linux?
That was Linux, yes.
Linux they have separate data structure.
They have a separate partition or file system for your swap. Other OSs do this as well, except Windows.
So a separate partition.
Separate partition on the hard drive, formatted specifically for storing pages, pages of a program that are in memory.